Hi, and welcome to Fixed Income Securities. Today we're going to look at credit risk, more specifically the structural model. The two major types of credit risk models are the structural models and the reduced form models. Structural models are more company-specific models where you use assumptions about the assets and the liabilities of a company to use option pricing theory. And this option pricing theory enables you to get an analytical answer to several problems within credit risk, for example, the probability of default. On the other hand, reduced form models use statistical methods to look at what kind of company-specific or macroeconomic variables can explain the probability of default. If you use the reduced form models, you need a good amount of data on your chosen variables in order to explain the default in a reliable way. But in this video, we are looking at the structural models. Now it's important to look at why we can use option theory when looking at the assets and debt and the equity of a company. Well, as you probably know from beforehand, the payoff from a call option on a stock is the maximum of the stock price in the future less the strike price and zero. So what does this mean? It means that if you have a call option, you're the holder of a call option, then in the future you have the opportunity to buy the stock for the strike price. So the value in the future is the stock price minus the strike price. That's your profit. And if the spot price is less than the strike price, then you choose not to exercise the call option. You choose to buy the stock in the market because you have limited liability. So you only have the upside, but you don't have the downside. If there is a downside, it's reduced to zero. And a similar limited liability can be seen as you look at the balance sheet of a company. The equity holders, they are in effect holding a call option on the assets of a company with a strike price of the face value of the debt. So what does this mean? It means that in the future, if the asset is worth less than the debt, then the company is bankrupt, but the equity holders, they can just leave the table and get away without a loss. The only thing they can lose is what they paid to get the equity in the first place. And if the asset value is higher than the value of the debt in the future at time t, capital T, then the equity holders can use the assets to pay off the debt, and they are left with the asset value minus the debt. So they are left with the maximum of AT minus DT of capital T and 0. Because the equity holders have limited liability, we can use an option pricing formula to value the equity. And the most famous formula for option valuation is the BLACK-SCHOLES-MERTON formula. What this formula says is that the equity value of a company can be calculated as a product of the asset value at time t times the standard cumulative normal distribution function of a number d1 minus the face value of the debt discounted with the time to maturity and the risk-free rate times the standard cumulative normal distribution given a number d2. Okay, and d1 is calculated as the logarithm of the ratio between the asset price over the face value of the debt plus the drift term, the risk-free rate times time to maturity, plus 1/2 of the variance. This is the yearly variance, the annual variance, times the time to maturity, divided by a scaling factor of the standard deviation times the square root of time to maturity. The D2 number is just D1 less the square root of time to maturity times the standard deviation. And this is the standard deviation of the assets. What's important to notice is that you only need 5 parameters or 5 inputs to the model. You need the asset price at time t, and you need the face value of the debt, and you also need the risk-free rate, the 1 year or annualized risk-free rate. You need the time to maturity of the debt, and you need an estimate of the variance of the assets. Another thing which is important is that this model was developed from equities, from finance, and given the opportunity to constantly hedge your position, as is often assumed in finance, you work in the risk neutral domain. And in the risk neutral domain, any stock has an expected drift of the risk-free rate and has a discount factor which is based on the risk-free rate. In this video, we are going to loosen up on that assumption because we are going to use the estimated drift based on the risk of the assets, and use those to calculate, for example, the expected loss and the present value of the expected loss. One thing we might need to explain more is this standard cumulative distribution function, the normal distribution. And if we look at the normal distribution, then we see that there are many normal distributions which differ based on their center and their variance, okay? Their mean and their variance. And what we are using here is this, the mean 0, variance 1. That's the red probability distribution. And the area under a probability distribution is always 1, okay? So what we are interested in is if we get a number, for example 1, what kind of area do we have from 1 and less, okay? So what we are looking for is the integral of this probability function from 1 to negative infinity, okay? And the cumulative distribution function actually gives us that. So we can see that if we have a value of 1, what's the probability that a random number will be 1 or less, okay? So then we just check here and we get a cumulative distribution function of maybe 0.85, okay? And we are not going to use these graphs, but we are going to use Excel later to find these values. So what does these factors actually mean? Well, the easiest one is the cumulative normal distribution given D2. It's actually the risk neutral probability of exercise of the option, which means it's the risk neutral probability of the asset value being higher than the face value of the bond at time capital T. On the other hand, ND1 is a bit harder to interpret. What you can say about ND1 is that it's called the delta of the option, and this is how much the option's value will change given a 1 unit change in the underlying, which is the stock or the asset value. And this is also the hedge ratio for the replicating portfolio based which Black-Scholes is based on. It's the number of stocks that you would use to hedge the option. What you can say about ND1 is that it's the present value of the receipt of the stock given that, or the asset, given that the value of the asset exceeds the future value or the face value of the debt. If we manipulate the Black-Scholes formula, then we can get an expression for the value of debt. So the value of debt is just a payment given default plus a payment given no default. So the asset at time t times the normal distribution function, cumulative normal distribution function based on the value negative D1 plus the face value of the debt discounted by the risk-free rate times the cumulative normal distribution based on value D2. You can see from the use of the D1 and D2 that this formula uses the risk-free or risk-neutral probabilities. What we are interested in is not the risk-neutral probabilities, but the risk aversion probability of default, for example. So if we consider risk aversion, then we have the probability that the asset value at time capital T is less than the face value of the debt. This means that there is a default. It's equal to the 1 minus the probability of no default, because if the asset value at time capital T is greater than the face value, then the equity holders can use the asset value to repay the debt. And this is equal to 1 minus n to the E2, or the cumulative normal distribution based on E2. And this is via symmetry. Some slides ago, you saw that the normal distribution is symmetrical. So 1 minus the normal distribution function given a number is just equal to the cumulative normal distribution given the negative of that number. And what is the difference between E and D, the risk neutral probabilities and the risky probabilities? It's just the drift term. Okay, so here we do not assume that we can create a perfect hedge. So we take the estimated growth rate of the assets and use those instead of using the risk-free rate. If we use these real-world probabilities, then we can find the real-world estimate of, for example, the expected loss. So here you have the future value of debt at time capital T times the cumulative normal distribution of negative E2. E2, the expression you saw at the previous page, less the asset value at time T, and you have to times this to e to the real world drift of the assets times the time to maturity times the cumulative normal distribution given the value of negative E1. So here you use the real world probabilities, but if you look at the present value of the expected loss, then you use the risk neutral probabilities. And what the present value of expected loss is just the value of a risk-free bond less the value of the risky bond. And I think an example would be in place here. This example is taken from Petit, Pinto, and Peri, 2015, page 294. Okay, so we are given some information, and that is the asset value is 1,000, and we have the expected return on assets, and we have the risk-free rate, and this risk-free rate is the drift in a risk-neutral world, and this expected return on assets is the drift of the assets given risk aversion. And then we are given the face value of debt of 700, and we have time to maturity of debt, which is only 1 year, and we have the asset return volatility, which is annualized. It's 30% per year. So now we can use the Black-Scholes formula, and we can count the D1, and this D1 comes from the Black-Scholes model, and here you have the logarithm, the natural logarithm of the asset value divided by the face value of debt plus the drift, which in the risk-neutral world is the risk-free rate, times the time to maturity of debt, plus 1/2 times the asset return volatility squared times the time to maturity of debt. All of this is divided by the product between the asset return volatility and the square root of time to maturity. Okay, so this is D1, and D2 is just, D2 is just D1 minus the asset return volatility times the square root of time to maturity of debt. And to get the probabilities here, or the normal distribution, we use the norm.dist function in Excel, and to get the n negative D1, we take the norm.dist negative D1, and we have 0, 1, and true. Okay, this will give us the cumulative distribution function, which is the probability for a standard normal distribution to contain a value less than negative D1, which is less than negative 1.37, and that is 8.5%. And we do the same here. We take the norm.dist function, and we take the negative of the D2, negative D2, and the parameters for this norm.dist function is 0, 1, and true. This will give us the cumulative normal distribution, and this gives us the probability of getting a number less than negative 1.07 from the standard normal distribution, and this is 14.18%. If we walk away from the risk-neutral world into the real world, then we can get the E1 and E2, and the only difference between E1 and E2 and D1 and D2 is the drift term. So here we use the expected return on assets, not the risk-free rate. So we use the expected return on assets here. And when we calculate these, and this is just calculated in a similar way as D2, then we can get the probabilities that the normal distribution, the standard normal distribution, would return a number less than the negative 1.43, and we have the same parameters for the norm.dist function to get the cumulative value. So we get a probability, a real-world probability of getting this number or negative this number or less. What's interesting with the probability given E2 is that here we get the probability of default. So you can use the Black-Scholes model to directly derive the probability of default. And this is calculated as the norm.dist given a number of negative 1.138, and these are the parameters to get the standard cumulative normal distribution, 0 mean and 1 standard deviation. And here you get a probability of default of 12.7%. We can also use the formulas we showed in the slides to get the expected loss. And the expected loss is just the face value of debt times this n negative E1 minus the asset value times the e to the 0.03, which is the expected return on assets, times the time to maturity of debt. And this is times n to the negative E1, okay? I think I made a mistake. This is, of course, times the probability of default, okay? So, if you plot in this, then you get the expected loss. And given an asset value of 1,000, face value of debt, and expected return on assets of 3% per year, the debt is maturing in 1 year, and the asset return volatility is 30% per year, then you have an expected loss of 11.78. The present value of the expected loss is quite interesting, because here you use the risk neutral probabilities. And so here you take the face value of debt and you discount it by using the risk-free rate times number of years times n to the negative d2, which we found here, and you subtract the asset value times the n to of negative d1, which we found here, and then you find the present value of the expected loss. And these two numbers, they generally differ because the present value of the expected loss contains both a risk premium and the time value of money. So whichever is bigger, you can see here. Here the risk premium is greater than the time value of money. If time value of money were greater than the risk premium, then the present value of the expected loss would be less than the expected loss. What's important to notice is that the present value of the expected loss is how much an investor would pay someone to remove the risk of default from holding this bond. So that was it for today, and see you next time.